Parts Garages. I'm speaking to you today from GE Oil and Gas Digital Solutions Boston Center, located in Billerica, Massachusetts. By introduction, I started with Panametrics in 1990 as an applications engineer. Since then, my responsibilities have included key account sales, segment marketing, services business development, and now product management. As product manager for the aluminum oxide moisture analyzer product line and for our analyzer's lifecycle services, I have been on a journey to transform the Panametrics and General Eastern product portfolios into a single, cohesive product line that you can rely on for your most critical applications. Today, it is my pleasure to present Moisture Sensor Calibrations, Good Habits for Great Results. Why would I choose this topic as a topic of my first webinar? Product quality, features, and specifications tend to predominate the attention of our customers, and this is where analyzer manufacturers tend to focus their attention. Lifecycle services such as spare parts, startup assistance, measurement audits, rentals, repairs, and calibrations translate the product attributes into reliable measurements. Today's topic on calibration will culminate in the benefits of implementing and maintaining a recalibration program for your trace moisture analyzers. To highlight the importance, we will review the moisture analyzer measurement technologies, calibration techniques, and the importance and benefits of calibration. We will leave ample time for questions at the end to address the topics most pertinent to your applications. The measurement of water vapor in gases and liquids offers challenges not typically found in the measurement of other process contaminants. Water molecules absorb onto metallic surfaces and accumulate in dead legs, fittings, and gaskets, and in filter elements. Changes in process conditions, such as an increase in temperature, will lead to off-gassing of these water molecules into the process gas, or will impact the measurement at the sensor. This adsorption will lead to long system dry down times. There are various methods employed to measure moisture. Metal oxide sensors, such as aluminum oxide, are often seen as good candidates for a calibration maintenance program. Most of the conversation will focus on these sensor types. Other technologies, such as tunable diode lasers, quartz crystal microbalance, phosphorus pentoxide, and chilled mirror, are often assumed to not need calibration. We will also touch upon these technologies and their recalibration needs. Common to all technologies, the sensor is only one component in the moisture measurement system. The measurement system includes the sample system, the tubing that transports the gas or liquid to the sample system, and the sample takeoff probe. Typical sample systems can include valves, pressure regulators, filters, and pressure and flow indicators. The wetted materials chosen, the integrity of the fittings, the selection and maintenance of the filters, and the age of the system all can offer opportunities to change the moisture content of the gas or liquid that reaches the moisture sensor element. Weaknesses in design, implementation, or maintenance may express themselves as calibration issues. Consider that all these system attributes may impact the accuracy and overall health of the measurement. All analyzers and their sensors are subject to process contamination that may impact speed of response and accuracy. Even the best sample systems are subject to process upsets, such as plugged filters, saturation with water, unexpected contamination, and leaks caused by vibration and or corrosion. All of these factors that may impact the measurement system can lead to the operator questioning the veracity of the sensor's readings. calibration of the sensor and analyzer enables the operator to clearly identify the weaknesses in the other parts of the system. It offers the opportunity to investigate and clear any of these potential issues. Before diving into the technologies, let's talk about verification, the complement to calibration. It is important to note there are differences between verification and calibration. Verification is intended to determine if the sensor is performing within specification, and if not, by how much. Calibration includes an adjustment so that the sensor can display the moisture measurement within its accuracy specifications. These are two complementary activities. Verification may be used to determine if a calibration or maintenance is required prior to the regularly scheduled calibration. Two common methods employed for verifying the performance of a dedicated moisture analyzer are portable moisture analyzers and in-field moisture generators. A portable moisture analyzer is a powerful tool to verify the performance of a dedicated analyzer. Since it can have an integral sample system, one can use a portable analyzer to troubleshoot the moisture measurement system, starting from the outlet of the sample system all the way back to the sample takeoff probe, until the root cause of the discrepancy can be found, or until this method verifies the measurement of the dedicated analyzer. The key to success is that the sample that passes the portable analyzer should be the same sample that passes by the dedicated analyzer, preferably in series, directly after the sensor to be verified. This method allows the operator to verify the measurement at the moisture content that is meaningful to the customer. Some prefer to use a moisture generator in the field to check their analyzers. Most moisture generation techniques are difficult to operate accurately at the point of measurement. In cases where this is possible, and these verification gases pass through the sample system and then pass the sensor, this method allows the operator to check the sensor's calibration at multiple moisture levels. It may be difficult to generate these moisture contents in the same background gas as the application or at the same pressure as the application. Some have had success with dual dilution moisture generators, permeation tube moisture generators, and with calibration cylinders, when great care is taken to control the environmental factors that can impact their accuracy. By employing one-point offsets or multi-point offsets, one may use verification techniques to calibrate the sensor or to adjust its calibration in the field. These techniques are not as accurate as laboratory techniques, where moisture generation and data collection are properly controlled. Any moisture measurement technology may come with external or integrated calibration and or verification devices with their moisture measurement system. These may include permeation tube or cylinder gas techniques. Permeation tube systems employ a desiccant to remove the moisture from the process gas or other carrier gas, resulting in a zero baseline. And then the permeation tube adds moisture to this gas to set a calibration point. There is no practical method to check the integrity of the desiccant. The system must also maintain proper control of flow and temperature. Great care is needed when using calibration cylinders, even when these are properly prepared with known moisture contents, typically no lower than 1 ppm. The quality of the gas can be subject to the ambient temperature, the length of time the cylinder has been stagnant, and the amount of gas remaining in the cylinder. Let's take a moment to recap what we've covered. We understand that the water molecule offers measurement challenges. The moisture sensor and analyzer are only one or two components in the complete measurement system. Verification and calibration can determine if or where there may be a measurement problem, and we have identified several methods of field verification, along with the challenges these techniques may offer in the field. Now let's look at some of the moisture measurement techniques. For each, we will look at the importance of the calibration and field verification. Aluminum oxide moisture sensors, along with other metal oxide sensing technologies, are the most versatile moisture analyzer technologies. They offer a very wide range of moisture measurement, allowing the operator to see the analyzer dry down from ambient moisture, typically in the 10 degrees C dew point range, or over 1% water vapor, to the measurement point of interest, sometimes below minus 100 degrees C frost point, or single-digit part per billion moisture contents. Due to their physics, metal oxide sensors change in calibration with time. Their installation in erosive or corrosive processes may accelerate this change. Contamination can make the sensor look like it is out of calibration. One can use portable analyzers and the verification techniques above to check the performance of the measurement system. Best practice is to perform calibrations at the manufacturer's facility on a regular basis. At GE, there are 7 steps involved in the calibration of the Panametrics brand aluminum oxide moisture sensors. 1. When the sensor arrives at the service center, the technician checks to see that it's operating. 2. Cleaning the sensor removes contaminants that could impact the calibration and future readings. 3. The lab technician installs the sensor into the calibration system. 4. The calibration system uses ultra-dry nitrogen to remove water vapor from the system and the sensors. 5. Water vapor is added in known amounts, and the system records each sensor's response at each calibrated point. 6. The system interrogates the data collected for a complete health check of the sensor, including signal, noise, and sensitivity. 7. The system generates a new calibration data sheet for the sensor and programs any associated electronics with this data. This procedure is used for the initial calibration and all subsequent recalibrations. Other manufacturers may have similar procedures. But what if you purchase an analyzer technology that doesn't need calibration? How does today's topic apply to you? There are several ways to answer this question. Let's take a quick tour of some of these technologies and explore either having a calibration program or at least a verification program schedule, how this can improve the measurement integrity. Tunable diode lasers are the newest technology introduced to measure moisture. This technology offers an analyzer that exhibits negligible change in calibration and time. These are immune to measurement errors due to most forms of contamination. This is not to say that the electronics that drive these analyzers can't be in fault. Changes in background gas can also impact the moisture reading if the background gas compensation algorithm is not sufficient. The cost of sending these back to the vendor's plant for calibration checks can be expensive due to the size of the analyzer. It is not practical to keep a spare analyzer on hand when return to the factory is necessary. To ensure these analyzers are operating properly, one may use a portable analyzer at the outlet of the measurement system. If the readings agree reasonably well, no action is required. If the readings do not exactly agree, and if the operator feels that the portable is providing the expected reading, some analyzers offer a 1-point offset. If the readings differ by more than the combined error budget, this is where further investigation is required. Whether using a portable or if the analyzer has an integral verification system, a regular verification program provides peace of mind that the analyzer is operating and is able to respond to changes in moisture. Quartz crystal microbalance technology has been in use for many years. This technology's accuracy is sustained by regularly adjusting its calibration, and thus these analyzers come equipped with an integral permeation tube-based 1 or 2 point calibration scheme. The permeation tube requires that the process gas be dried below the calibration point to be generated. This can be considered the zero gas. This is accomplished by using a desiccant. Since there is no practical method to check the integrity of the desiccant, an operator could doubt the integrity of the calibration scheme and thus the measurement. A portable analyzer at the point of measurement can confirm that this analyzer is in calibration and properly responding to changes in moisture. If, for example, the reading from the portable is wetter than the dedicated analyzer after equilibrium is attained, this may be an indication that you need to replace the desiccant. These desiccant cartridges are a standard spare part. Since spent desiccant will result in drier than anticipated readings at the analyzer, a regular verification program will help identify a false sense of security. Phosphorus pentoxide moisture analyzers are popular in certain moisture measurement applications. The theory is that the P2O5 desiccant absorbs the water vapor, and the analyzer converts this to hydrogen and oxygen. Anything that can change the ability of the P2O5 to absorb moisture will impact the accuracy of the measurement. Many consider this a first principle method. Thus, they state that the sensor requires no calibration. At least one manufacturer states that the P2O5 is slowly consumed, eventually rendering it unable to respond to moisture, and that the sensor needs to be recoated. Since the P2O5 desiccant isn't a perfect desiccant, a regular verification schedule will provide indication of when the imperfection impacts the accuracy of the analyzer. One can use calibration cylinders or a portable analyzer to ensure that the real-world sensor and measurement system behave as physics would dictate. Chilled mirror moisture analyzers are a primary measurement device, as they measure the temperature at which dew or frost reach equilibrium on the reflective surface. Given that these devices are often used as reference standards for the calibration of other devices, it is best practice that these be calibrated on a fixed schedule. This is typically accomplished at the manufacturer's facility or at accredited calibration labs. Contamination can impact the performance of this analyzer, as can fault with the thermoelectric coolers. In the field, these can be verified using any of the previously mentioned techniques, especially when these are used in industrial applications, as opposed to clean and controlled laboratory environments. This is not a comprehensive list of all the trace moisture technologies. Calibration or verification requirements for other technologies can be similar to those previously mentioned, with similar benefit. Think of calibration as an insurance policy for your moisture measurement, not just a good habit for your sensors. Proactive calibrations instill confidence in the measurements and in the processes that these measurements enable. Reactive calibrations are typically initiated when the operator is questioning the sensor readings. This is not a good starting point for any investigation. It is easier to blame the sensor as opposed to the measurement system or the process. There is no more compelling way to describe the benefits of regular calibrations than actual customer experiences. This customer story comes from personal experience when I was an applications engineer. a natural gas transmission company would send in aluminum oxide moisture sensors for calibration only when the moisture readings were deemed untrustworthy. Readings from these sensors were often compared to a standard sensor installed downstream. To minimize the possibility of damage or loss in transit, the technician did not send back these standard sensors. Increasingly, he found that the recalibrated sensors would read wetter than expected and reported what he felt were false positive readings. At the same time, the standard sensors would hold constant at a significantly drier moisture reading. To help resolve the discrepancy in readings and the ensuing differing opinions between the maintenance and operations teams on the reasons for the discrepancy, we were able to convince this customer to send in their gold standard sensor for calibration. When the package arrived, the calibration lab called me down to visually inspect the sensor. I carefully removed the protective shield to find no sensor attached to the posts. After calling the customer and asking him to power on his analyzer, now, of course, with no sensor attached, he was surprised to see that the analyzer was still reading the same it always read. In this case, two faults had occurred. The customer had installed the moisture probe without a sensor. This was intended to be used as a temporary plug for their sample cell and sample system. And the cable to the analyzer was not properly shielded, causing it to read a rather steady offset that only varied with environmental factors. A regular calibration maintenance program would have revealed this problem much earlier. The customer checked all points of measurement with a portable analyzer, cleaned up the installation of those that had issues, gained confidence in their measurements, and then went on to a maintenance program governed by their ISO procedures. This customer experience shows us the value of verification, regular calibration, and that the entire system should be investigated when issues arise, in this case, the interconnecting cable to the analyzer. Now let's talk about where to perform those valuable calibrations and how to manage them. The manufacturer of your moisture analyzer took great care to properly calibrate the moisture sensor when you ordered this new. They have the proper facility, data collection tools, and programming tools. Most often, returning the sensor or analyzer to their facility is your best option. They should be able to provide you a report detailing the change in calibration from the most recent. GE saw the value, as Panametrics had, to localize this calibration support, making it easier for customers around the globe to take advantage of this type of calibration in their own region. GE has computer automated systems to calibrate Panametrics moisture sensors in the greater Boston, Shannon, Tokyo, Abu Dhabi, and Changzhou metropolitan areas, with smaller systems in Brazil and in India. Third-party calibration facilities either offer the convenience of local calibration or they offer lower prices. At times, this may be a viable alternative to factory calibration. Some are not able to meet the original specifications, are not able to give a comparison of calibrations against previous calibrations, or the procedures did not match the requirements of the sensors they calibrate. To show where using a third-party calibration facility can complicate troubleshooting activities, let's take a look at another use case. This is from a recent and ongoing customer experience. A customer outside the U.S. was having questions concerning the performance of their moisture sensors. Since they had a local company willing to do the calibrations at a lower price, they sent their sensors to the local in-country laboratory. The lab suggested that the sensors had changed significantly in calibration, but even after recalibration, these sensors did not perform to the customer's expectation. The question of the role of the third-party calibration facility was an obstacle in getting to the root cause of the issue. Since the customer had success with our sensors in the past, we sent them new sensors. and the cycle of doubt repeated itself. After months of frustration, a deep dive determined that the calibration procedures the local lab was using did not allow for a proper dry down to baseline, nor for proper dwell times to the different moisture levels, nor were they able to produce any traceability of their calibrations to accredited standards. We are now working directly with this customer, with their probes, and on their applications to determine why these sensors are not performing to meet their expectations, without the added complexity and uncertainty of a third-party calibration coming between us. Now that the sensors are coming back to us, the physical evidence shows that something in the application is attacking the sensor, changing its calibration. This could not have been resolved as long as the sensors were not coming back to the factory. The customer stories above give good examples of why a regular calibration program yields the most accurate measurement, enables the ability to properly identify the root cause and performance issues, current or pending, and builds confidence in the measurement system. For technologies such as aluminum oxide, removing the sensor and sending it back to the vendor for a calibration provides significant benefits. The sensor is cleaned and recalibrated in the same system that performed its initial calibration. Unlike in situ verification and third-party calibration, calibrations at the vendor's laboratory remove the moisture generation system as a variable in comparing past performance to present performance. Taking the measurement system offline to send sensors in for calibration provides the technician a regular opportunity to check the filters, leak check the system, and allows for a physical inspection that may lead to other areas of improvement in the measurement. Why not just buy a new sensor instead of returning these old sensors back for calibration? Sensors acclimate to the process that they are exposed to. This, along with the natural aging of the sensors, leads to better calibration stability with time. For these reasons, whenever possible, regular calibration at the vendor's calibration facility will lead to a better measurement than replacement with a new sensor. You don't have to manage your sensor calibrations on your own. GE offers several types of calibrations, many types of sensor configurations, and with a global perspective to calibration services, understands that there are regional and cultural differences in how to best help our customers. Our customers have used many methods to track and manage their moisture sensor calibrations. Some methods may be better than others. Many use Post-it notes, whiteboards, and notebooks on people's desks. We all love the 1980s. We no longer use rotary dial phones, nor should rely on scraps of paper. Some companies use calibration stickers. These are passive devices. In the field, the sticker has no ability to call out for service, nor to provide insight as to the criticality of the measurement. We offer analyzer firmware reminders to provide visual indication of the need for calibration. The technician will still need to refresh the calibration dates in the analyzer upon installation of new sensors or recalibrated sensors. In the above cases, there is no relationship with the vendor, leaving the customer on their own to ensure the maintenance and calibration of the sensors. More can be done. The vendor may choose to send out calibration reminder letters from their service center. This requires accurate installed base information correlated to the product's calibration dates. These letters nicely complement the various offerings, as the vendor now has a relationship with the sensor's technician. MRP systems such as SAP and Oracle and other software programs can provide reminders. When the customer has this capability, even though it is on their own, it typically ensures regular calibrations. GE provides a secure portal where the user can assign their sensors to their plant and get email calibration reminders. With the instrument calibration portal, the user dictates how often the calibration is required based on measurement criticality. This is ideal for smaller companies that do not have expensive software systems. The most impactful relationships occur when the vendor and customer agree on calibration schedules. The vendor manages the customer's spare sensor pool and sends the customer's recalibrated sensors to the plant in advance of the need. GE has the most success with the moisture sensor exchange program with our larger customers, especially those with a fair number of sensors in critical applications. We ensure that the customer receives their own sensors and transmitters. These are not refurbished products nor previously installed at unknown customer sites or applications. The greatest success occurs when a more intimate relationship exists between the vendor and the customer. This is when customers ask us to hand-deliver recalibrated sensors and install them and inspect the system as part of a complete measurement audit. The GE service engineer will then return the customer's sensors to the service center, segregated from other customer sensors, where the sensors await their future calibration and return to process. In these cases, the customer and the manufacturer share ownership in the success of these moisture measurements. At GE, we have known that good calibration habits lead to great measurement results. Our customers have proven this to us time and again. We hope that you have found this presentation to be informative and that you may implement some of these ideas to improve your measurement systems. Thank you for your attendance. You may find much of this information covered on the GE Oil and Gas LinkedIn page, my personal LinkedIn posts, and you can follow me or GE Oil and Gas on LinkedIn for regular updates on moisture measurement topics. Let's take some of your questions.
To submit a question, use the Q&A feature. We will start with the several that came in during my presentation. First one that came in was, how cost-effective is it to recalibrate a probe with the manufacturer if the manufacturer is located on another continent? That's a great question, and we touched upon it in the webinar. That's where it's incumbent upon the manufacturer to make that facility available much closer to the customer. When it's still not possible or was not close to a calibration facility, there is the cost and there's the value. Yes, the cost can be high to return a probe outside of a country when you're paying taxes and fees and tariffs, etc. And of course, there is the cost of the calibration itself. But as the sensors do age with time and become better sensors and better measurement sensors, it is still recommended you do that, even if the cost of recalibration starts to approach the cost of a new probe. So we highly recommend returning the sensor to the calibration facility, the vendor's calibration facility, even if it is in another continent. At the same time, keeping a set of spare sensors cycled for those calibrations at least makes it easier from a time perspective so that you're not without a measurement when you need one. And that's where keeping track of that is an important function, and that's where certain tools can help, whether it be things like Instrument Calibration Portal in order to track your calibrations when you need them, or whether an exchange program might work locally. We have another question. What is the optimal interval for calibration, and does it vary by application? If we focus on aluminum oxide as an example, the optimal interval is based on the importance of the measurement, the importance of the accuracy of the measurement. As an example, if you're monitoring moisture in instrument air, you have a great drying system, you don't have many upsets, and the sensor is operating at that point, one might say even though a recommended interval is a year, you could push that out to a year and a half between calibrations. On the other hand, if accuracy is important and it's vital that you know within the accuracy of the sensor what that measurement is, because your dryer might be just within a couple of degrees dew point of what your needs are, then I would say you would pull that calibration in, whether that's annual or every 6 months. Additionally, if you are governed by another agency like the FDA, the Food and Drug Administration, where you must calibrate your device in a certain time interval, then of course that would take precedence. In that case, it's mandated by legislation or by regulation that it be calibrated every 6 months. For more strict applications like hydrocarbon gas, hydrocarbon liquids, our recommendation is 6 to 12 months. Typically 12-month cycle is adequate for keeping the sensor healthy and keeping the measurement online. So this is the balance between keeping the measurement online and keeping the measurement healthy. We have another question. What is the shelf life for my aluminum oxide moisture sensor? Let me see how I can address that. So shelf life, the sensor will be fine. It can stay on the shelf in a box as long as you need it to. There's no harm, no foul. But its calibration is changing with time. Even though it's still in a box, it doesn't know that it's in an application, not in an application. As far as it knows, its application today is to measure the moisture content inside the box. So it doesn't have smarts enough to say, oh, I will or won't change in calibration just because I'm sitting on somebody's shelf. And again, that's where a good calibration program helps, is that you probably don't want freshly calibrated probes sitting on a shelf. What you probably want is those freshly calibrated sensors in your application. The ones that are slightly out of calibration could either be on the shelf as a backup or in rotation going back to the into the factory for calibration to be put in another application. There is a benefit, obviously, of keeping sensors in their own applications, but if you're looking for strict accuracy and recent calibrations, cycling them through is not an issue. That is something that is fine for the customer base. So we, in terms of how long will the sensor last, if that's what shelf life means or lifetime of a sensor, short of mechanical failure, there is no anticipated lifetime for an aluminum oxide sensor. It is not consumed by being operated. It is not consumed by being on the shelf. So we've had sensors come back for calibrations for over 20 years. Sensors that we shipped back in the 1990s and in fact even 1980s are still in service today, and that's a testament to the calibration program and cycle that the customer has put in place. It's also a testament to the sample system design and operation of the sample system as it keeps the sensor from being exposed to contaminants, erosive or corrosive items. So from a shelf life perspective and a life cycle perspective, I would say that there is no detriment for keeping the sensors. Another question just came in. When an aluminum oxide sensor is recalibrated, are any adjustments made to the sensor? So for our sensors, the answer is no. There is no potentiometer that we tweak to bring in the zero or the span. The way that the GE aluminum oxide sensors are calibrated is that they're exposed to various levels of moisture, and we're recording the output of the sensor at those levels of moisture. So in essence, what we're doing is we're characterizing the response of the sensor. So at, let's say, minus 50 degrees C test point, we're waiting for the sensor to come into equilibrium at minus 50 degrees C. We're recording the raw value, the raw signal from that sensor, and that's what actually gets on to the calibration data sheet or programmed into the sensor electronics. Therefore, if you're seeing minus 50 degrees C on the Dewpoint analyzer, you know that's what the sensor was exposed to before. That's the response the sensor is seeing. And that's great news for you, because we haven't adjusted it to make it read minus 50 C. We've actually done it the other way around. We've actually measured minus 50 C and made available that opportunity to take and show you that display right there. So yeah, the raw signal dictates the calibration. So it's really a characterization more than it is a calibration. I have another question here. In the presentation, you mentioned that there are various types of calibrations. What types are you referring to, and why would there not be one type? Calibration is intended to mimic, to some extent, the application the sensor is in. So therefore, if the sensor is always exposed to ultra-high purity gases, very, very dry gases, and it's there all the time, and then you have excursions to other alarm points or past alarm points that you're very concerned about, the calibration ought to mimic that as much as possible. Therefore, for ultra-high purity applications, whether they be for semiconductor applications or, for that matter, applications where the sensor's after emulsive dryer and the accuracy is of importance, great importance, that it's not just there to trend and to alarm on rate of rise, we have what's called a low-end calibration system. In this case, we're exposing the sensor ultra-dry moisture levels for weeks before we start generating any moisture contents. The whole calibration system is in a different state than it would have been had we been purging it only for a week. So the whole system is in a different state, and then we generate frost points as low as minus 100, minus 90, minus 80, and we wait for equilibrium to occur at each of those points. That's a very specialized calibration for a very specialized application. Another type of calibration we offer is a high temperature calibration, where we do our standard calibration at high temperatures in case the system is basically being held at those high temperatures. Again, your sample system and your calibration system are now being mimicked the same way by keeping them at that higher temperature, and therefore the sensor response is going to be measured at those higher temperatures and giving you a much more characteristic response than it would have been had you calibrated the sensor in a standard calibration system. Again, in both those cases, whether it would be an ultra-dry application or a high-temperature application, both the moisture content and the temperature are impacting the entire measurement system, and therefore we want to emulate that in our calibration system. I have a question here. How should maintenance engineers perform maintenance on the probe? Is a purge with nitrogen needed? The only time that the only circumstances under which we recommend a purge with nitrogen is if you have a highly erosive or corrosive application, and you do not need an online measurement 100% of the time. So as an example, if you wanted to measure moisture in chlorine gas, and the chlorine gas could be wet, then the wet gas could be corrosive and either change the calibration of the sensor quicker than you might like, or might actually damage the sensor. But if the measurement's important, you might keep the sensor on nitrogen purge and then switch back and forth between that and the process gas in order to make a spot check to make sure that you are, in fact, within your process limits. Okay? Another time where a nitrogen purge might be useful is if you know you're starting up an application, you know the process gas is wet, and you want to avoid saturating the sensor right from the beginning. In that case, keeping the sensor on a nitrogen purge, in fact, keeping the entire sample system on a nitrogen purge, keeps the system dry. And when you're ready to make that measurement, when you know your system is online, when you know you're not expecting to have gross amounts of water in your system or contaminants in your system, you can switch away from nitrogen purge and go to your process gas. The same is also recommended if in fact that process gas might be slightly corrosive and slightly dry, or very dry, and now you want to take the sensor out of the sample system to return it back to us. One thing you could do is put it on nitrogen purge to remove the contamination from the sensor or the corrosives from the sensor before exposing it to ambient air, which would be very wet. In fact, that is one of the leading questions that we get when we receive a sensor back and it's maybe failed calibration, and the customer says, well, it worked fine in the application. And the question becomes, well, what was the application? If it was corrosive or erosive and the sensor was pulled out of process and it was then went from dry to wet with the corrosive right on there, damage could have occurred in transit. So that's where a nitrogen purge would be great as a maintenance program. Next question was, is the initial calibration at the manufacturer performed with a sensor or a sensor filter on the probe? There is a 100 micron sintered shield that protects the sensor when we ship it, in the cases where we're shipping it for gas applications. And there is a sheath, a stainless steel sheath for liquid applications. That is installed during the calibration. So it's there to protect the sensor as it's being handled in terms of our calibration. And then for you in the field, it's there to protect you from having that also cause mechanical failure by bumping the sensor against the sample system wall, etc. So yes, the initial calibration is performed with the sensor filter in place on the sensor. Next question is, when comparing other technologies with aluminum oxide as a portable, should you compare Dewpoint or PPM? That's a trick question to some extent, because the sensor is calibrated in Dewpoint. The analyzer that you're displaying could be in PPM. So now you have a mix of measurement units. What I would say is you should look at the portable in Dewpoint, convert it to PPM, or actually vice versa, convert the other technology to Dewpoint, and see that you're falling within the accuracy specification of the portable. As an example, if you're expecting a Dewpoint of minus 60 degrees C or 10 ppm, okay, so the analyzer that you're testing is reading 10 ppm, and the portable is reading minus 60 degrees C at the same pressure as the other analyzer, then you know they're within their accuracy specification, because minus 60 degrees C Dewpoint is equal to 10 ppm at atmospheric pressure. If in fact it reads minus 58 or minus 62, you're still within the accuracy of the portable and probably within the accuracy of the other analyzer, but now it could be somewhere between 7 and 12 ppm if you were just looking at ppm on the portable. So the answer is yes, compare it both in Dewpoint and in ppm to be assured that you're within the accuracy budget of both analyzers. Probably the best question so far. If readings are different, does it mean I need to calibrate one of them? If in fact you have different readings, you have to try to understand what may be the cause for the different readings. If we've in fact addressed all issues around the measurement system, in other words, filters are clean, fittings are tight, the system is well built for the application, and now the portable and the analyzer are out of specification of the total error budget, it's a good indication that something needs calibration. So for instance, if in fact the portable is one that you own it and you maintain it yourselves, and you have multiple probes, always use the most freshly calibrated sensor when trying to verify the performance of the analyzer in question. At the end, if in fact the portable you have faith in and there is still a discrepancy in readings, it would be a good indication. A good next step would be to calibrate the unit under test, the one that you're questioning. Okay, for natural gas applications, the standard in Mexico is 100 ppm. How long will aluminum oxide last before calibration? Well, again, the question is probably best stated is how much do we expect for a change in calibration with time in a natural gas application where the standard is 100 ppm. Just to give everyone context, in cold regimes, the dew point is, or the moisture content expected is around 2 pounds of water per million standard cubic feet of natural gas. As you get into warmer climes, it's 4 and 7. And at 7 pounds of water, you're at or around 100 ppm. The sensor is expected to change in calibration by around 2 degrees C dew point between 6 and 12 months. It will change less in dew point in calibration due to contamination as long as you have a well-designed sample system. So let's assume that the sample system is well-designed, the sensor is installed properly, and it's reading 100 ppm, or the tariff is 100 ppm. Most likely your application is not actually at 100 ppm. Most likely your dryers are drying well below that. So there is the 2 degrees C change in calibration within 6 to 12 months is not going to be impacting the sensor's ability to measure at 100 ppm appropriately. In most of these applications, what you will see is that you will remain below the tariff limit, and then only under upset conditions do you see it spike up at or near it, or quite often it doesn't come up to the 100 ppm limit. It typically goes right past it. So the calibration cycle there is not impacted. So whether you're in a cycle of 6 months or 12 months, you should be fine. If in fact your dryers are running at or around 100 ppm and your tariff limit is 100 ppm, then obviously in order to maintain the highest level of accuracy, which you now require because you're running so close to your alarm point, the more frequent calibration is the better calibration. In that case, I would say don't go more than 6 months or 8 months between calibrations. What types of accreditation should I look for when evaluating a calibration facility? That's a great question. Always, bar none, minimum should be a national accreditation. So in the United States, we'd be talking about the NIST, the National Institute for Standards and Tables. If you're in another region, like in Japan, it would be AIST. You want that as a minimum. What that gives you is the assurance that the equipment that's calibrating the sensor is also calibrated on a regular basis, that there's record keeping, and that there are procedures in place to allow you to repeat that calibration over and over again. For a higher level of calibration, there are standards such as ISO 17025, which go more towards data retention, and again, talks more about the repeatability of the system and the ability to calibrate and recalibrate and stay within the calibration spec for that sensor. Typically, ISO 17025 calibrations take a little longer to perform. In essence, you're doing 2 calibrations. You're doing a calibration and then a verification of the calibration to ensure that the sensor is now leaving within specification, it's operating properly, and the calibration systems have been operating appropriately during the calibration of the sensor, both as an initial calibration and then as a verification on that calibration. And those calibrations and those standards should be followed both for the manufacturer and for the recalibrations down the road. So you want to buy sensors from folks who have those accredited calibration systems, and you also want to be able to ensure that when you send them for recalibration, at a minimum, that those systems are in fact accredited also. Refer to your regional standards to understand where you are there. Thanks again for joining. We had quite a few really great questions. I know we couldn't get to all of them in the time that we had allocated. We will be following up after the webinar with questions that were not answered. And we thank you for joining us today and wish you a great day.